So what do you suppose we are seeking to find given the differential equation?
What's changing?
Well, yeah, so you should keep in mind that a derivative can be used to represent a rate of change, okay? So a lot of the applications of differential equations deal with rates of change. So I know for sure, I heard electrical engineering, so I'm not too familiar with the material there, but I know that differential equations are used pretty regularly. Chemical engineering, I know that there are some things like rates of reaction all comes from differential equations. Economics has some modeling done with differential equations. It's actually, differential equations are a pretty powerful tool to model things. I mean, if you think back to algebra, most of the word problems or the applications were pretty contrived. They're not the sorts of questions that you ask yourself in real life, but differential equations can be used to answer all sorts of interesting questions in real life. So here's a simple one. First stage. Nothing. Okay, so here's a simple differential equation. This one's pretty easy to solve. What do you think we're looking for? What's unknown here? What is the dependent variable, right? So the dependent variable should be a function of the independent variable. Okay. So generally speaking, the goal is to find some function that satisfies this equation. Okay. Now it's not always going to be the case that a function per se satisfies the equation. You could have some relationship, like a solution could look like. So this has nothing to do with this, but you may find a solution that looks like this. Right, so this tells you something about y, but y isn't a function of x. You see what I mean? So generally speaking, we're seeking a function of the independent variable, but that might not always be the case. So more generally, we're seeking some relationship between the dependent variable and the independent variable. Right, so how do we solve this equation? How could we determine y? So you have to be careful. Remember that this is called Leibniz notation. It looks like a fraction, and in many ways it acts like a fraction, but it isn't a fraction in reality. So let me just say, the fundamental process of equation solving is to undo operations, right? So to undo a derivative, you have to integrate, right? So for this simple differential equation, one where the derivative's been isolated, you can integrate with respect to the independent variable. Okay, so what is this? The integral of the derivative of y. Yeah, fundamental theorem of calculus says that that's just y, right? So y equals this.
X squared plus c.
Yeah, so the antiderivative of 2x is x squared, right? But this is just one of the antiderivatives, right? So, what do you differentiate in order to get 2x? Well, you have to have x squared, but then you could also have, in addition to that, any constant, right?
Right.
So the general solution to this differential equation is x squared plus c, okay? So this is usually the case. I've got some comparisons between algebraic equations and differential equations, right? So an algebraic equation, every variable represents some unknown quantity, right? So an equation is a relationship between those quantities. If you have a differential equation, we have a relationship not only between fixed quantities, but also rates of change, okay? So it's a relationship of two things, fixed quantities, well, I guess they're variable, but they represent quantities and rates of change, right? So, this might look like an unusual solution, right? If you solve an algebraic equation, generally speaking, you get a single number, right? X equals 4, or something like that. If you have multiple variables, you can get an ordered pair or triple of numbers. So almost always, sometimes there are trivial differential equations whose solutions are constant, right? But generally speaking, a differential equation is going to be a function, or sometimes it will be a relationship, okay? So whereas in algebra you're seeking numbers as solutions, here we're seeking functions or relationships as solutions, okay? You know, and if you have some algebraic equation, like think of a polynomial equation, say fifth degree polynomial equation. How many solutions would you expect to find? You'd expect to find 5 solutions, right? So almost always you find some finite number of solutions, right? If we're fundamentally going to integrate in order to find the solution, we're always going to introduce these constants, okay? So this is a solution for c equals 0, c equals 1, c equals 2, and so on. So we will almost always, in fact, I think we will always find an infinite family of solutions, okay? All right, so today we're just going to talk about some terminology that won't most of this won't necessarily be important to us. I just want to make you aware of what all is out there, okay? So we have 2 types of derivatives, right? We have the derivative, which you might call the ordinary derivative. For those of you who took calculus, which derivative did you experience there? It's a partial derivative. Right. When do you find a partial derivative versus a regular ordinary derivative? What's that? I think you're on the right track.
So,
We have more than one variable.
If there is more than one independent variable, then you can only find partial derivatives. You can't find ordinary regular derivatives, okay? So partial differential equations is a completely separate class. So we are not going to do solve any partial differential equations in this class. So what does that mean for you? That means that there's always going to be only one independent variable, okay? Later in the semester, we will discuss how to solve systems of differential equations. So there we will have multiple variables, more than 2 variables, but only one will be independent, the rest will all be independent. All dependent. So I gave you a couple of examples. So the one on the left, why is that an ordinary differential equation? Because only ordinary derivatives appear. And why is that? It's because there's only one independent variable. Can you tell me what the independent variable is? It's t. How do you identify the independent versus dependent? Dependent's always on top, independent's always below. Okay. The one on the right, obviously, is a partial differential equation because it contains partial derivatives. That is a completely separate class on its own. Okay. So another way that we'll classify differential equations is based on the number of derivatives that are taken. You can sort of make an analogy with the degree of a polynomial equation. So what's the degree? It's the highest exponent that appears in the equation. In the same way, we'll classify differential equations based on the highest order of derivative that we find, and we'll call that the order of the equation. Okay, so who can tell me what the order of this equation is?
third order?
Yes, it's here. This is the third derivative of y minus, and then here, don't be fooled. This is the first derivative raised to the 4th power, right? So this has order 1, and then plus y to the 5th. Okay. Here, I guess you could say that the order of the derivative is 0, right? No derivative's been taken. So 3, 1, 0, the highest order that appears is 3. Okay, so this is order 3. Okay, so for the first third of the semester or so, we'll be concerned only with first order equations. You know, as you can expect, the higher the order becomes, the more difficult it is to solve. So we're going to have to vastly limit the types of equations that we solve when we increase past order 1. Okay, so we'll solve a wide variety of first order equations. We'll solve a limited variety of higher order equations. Okay. So the the next way that we classify, it's a little difficult to say in words. So you can look at what the textbook definition of what it means to be linear is. What in general, what do you think when you hear the word linear other than line? You would. I took the easy one, right? What does it mean to be linear in algebra? Do you know?
Just
Like what makes an equation linear?
no powers. I guess.
No powers, yeah. So that's one, right? The other things, like you can't involve transcendental functions like sine, cosine, logs, and those sorts of things, right? No roots, none of that. So
Or just y equals x.
generally speaking, y equals x, you could have multiple variables, right? You could have a linear equation with 3 variables, right? 3x plus 4y plus 6z equals 4, right? This is a linear equation in 3 variables, so every variable that you see is on its own, not raised to powers, right? This would not be linear, 3xy plus 4z equals 1 because you have a product of 2 variables, okay? So it's the same sort of idea in differential equations, but we have multiple variables. Most of the time, we're only going to have one dependent, one independent, okay? So the way that you can think of this is any occurrence of the independent variable you can ignore. Okay, so if you look at the textbook's definition of what it means to be linear, let me write it down. So a sub n of x times, this means, remember the parentheses, the nth derivative of y plus a n minus 1 x. Can anyone make any sense out of what this means? What is-
said that the x?
What is this, do you know? What does this mean?
It's the starting line.
Well, I mean all of these, a sub n of x, a n minus 1 of x.
Isn't that like a coefficient?
It's like-
It is a coefficient, right? But that's also function notation, right? So you should understand that to mean any function of x, okay? So no matter what you see regarding the independent variable, it has no impact on whether or not the differential equation is linear, okay? So we'll call them coefficients. They won't be constant coefficients. They're variable coefficients, okay? So it's any function of the independent variable, then multiplied by some derivative of the dependent variable, okay? So in each term, you should only see one occurrence of the dependent variable or its derivatives, and then nothing else. So you can't raise the derivative to a power, you can't evaluate a function with it, a cosine of y prime or something like that, okay? So each term contains only one occurrence of the dependent variable, and then nothing else other than functions of x, okay? So let's see if you can tell me. So A, is that a linear differential equation or non-linear? This one is linear, right? The first term is only y prime, second term is only y. The x on the right-hand side, you can ignore, okay? So A is linear. B?
Non-linear.
B is non-linear because it involves a product of dependent variables, okay? C?
Non-linear.
C is actually linear.
Oh, really?
So sine of x might tempt you to say that it's not linear, but x is the independent variable, sine of x is the coefficient of y on its own, so C actually is linear. You see what I mean?
Oh, so but in D it would be.
So basically, any independent variable expression you can ignore when you're checking whether or not the equation is linear or not. Okay. D.
Non-linear.
This one's non-linear, so this time it's sine of y, okay? So, so since it's the dependent variable evaluated for some function, that makes this non-linear. I threw a bunch of nasty looking stuff in there in order to trick you. But if you remove anything that contains x, first term has only dy dx, the derivative, right? Second term only contains y. Right-hand side has no occurrence of the dependent variable whatsoever. Okay, and I shouldn't have put an equals 0, I should write can be equal to any function of x. Okay. So E is actually linear. Okay, and then F,
Just non-linear.
nonlinear, y raised to a power, so nonlinear. Okay, get the idea? The only time that you'll really need to determine whether or not something is linear versus nonlinear is in the first, I guess I should say chapter 2. So we're only going to be identifying linear versus nonlinear in chapter 2. So some of them will be, some of them will not be. Okay. After chapter 2, when we move on to higher order equations, all of those equations that we're going to be considering are going to be linear. Okay. So we'll move between, I have 3 pieces of notation listed. In fact, we'll be using 4 pieces of notation, but I'll talk about the 4th later on. These 3, at least the first 2, you should certainly be familiar with. Right, so the first, prime notation. Okay, so you use an apostrophe in order to indicate the derivative. You know, usually after you get past the 3rd derivative, you start using this notation instead of the tick marks so that you don't have too many to count. So as an example, y prime equals pi equals 0. I would say all of these notations have their advantages and disadvantages. If there was no advantage, then we wouldn't use it anyway, right? So what versus the other 3 do you think is the advantage of this notation?
Quicker.
It's quicker. This is the simplest to write, right? So the biggest advantage is that it's the simplest to write, right? So it's simple, but what's the disadvantage to this notation?
You don't know what variable it's.
Very good. It's ambiguous. What's ambiguous about this?
I know with respect to.
Yeah, I know that the dependent variable is y, right? But we don't know what the independent variable is. Okay, so that's fine. You know, if you encounter something like this, you can call it x or t, or whichever letter that you like. But one of the drawbacks is that it's ambiguous. Okay, so 2 is Leibniz notation. Okay, so I'll write exactly the same differential equation using different notations. So it's dy dx plus y equals 0. Right? You can basically reverse the advantages and disadvantages here, right? So this one is complicated to write, but it's very clear, right? So it's complicated but clear. Okay, the 3rd is differential notation. How many have seen this before? Because I wasn't looking at it. Raise your hand. Just a couple of you. So you may have seen this
Right there.
once or twice and not remember it from calculus. I can think of just a couple of times when you find like the total derivative and other things like that. So we'll be using this pretty regularly in the 2nd chapter. So this is the same equation, dy dx plus y dx is equal to 0. How do you think I've moved from here to here? Looks like an
Just
algebraic manipulation.
Right.
Right. So you can think of like multiplying by the denominator, which is dx, right, to move from Leibniz notation to differential notation. Okay. So like I was saying earlier, this thing acts a lot like fractions act. Have you seen some of the ways that you can use Leibniz notation to represent rules in calculus, and it appears that it's acting like a fraction. Like the chain rule.
Yeah, that's it.
You ever seen the chain rule with Leibniz notation? dy dt, there's some intermediate variable, x. This is the same as dy dx times dx dt. So this is the chain rule in Leibniz notation. It looks like these are fractions, right? There's also the derivative of the inverse, dy dx is equal to the reciprocal of dx dy. This is the derivative formula for the derivative of the inverse. It appears that it's acting just like a fraction. Okay, so in some sense it is, right? I mean, the derivative comes from the difference quotient. Then there's also a limit involved, so you have to be careful with confusing these things with fractions. And many times they act like fractions. There are instances where they do not. But we are going to pretend that they're like fractions in order to move from this notation to this notation. Okay, who knows what this means though? dy.
Change in y.
Change in y is this. They're related to each other, but they're not quite the same. Anyone know what the difference is between dy and delta y? I mean, delta y just means some future value, y final minus some initial value, right?
Is it a change in y over a hypothetical discrete point?
What do you mean by a hypothetical
Like
discrete point?
something that you can't define, that's just a discrete point. Like if it's a change in y, it's a change in a finite final minus a finite initial. But this is just a,
Yeah, I mean,
Not
if you're thinking of like the value of y at two different x values, right? So you can find the value of y at x equals 1, find the value of y at x equals 2, and take their difference, that's change in y, right? This is an infinitely small change in y. So it's like the initial and final point are the same, right? So if you think about the difference quotient, what do? You let the change in x go to 0, and that produces, these are called infinitesimals, okay? So you should think of it as an infinitely small change in y, even though that's technically not realistic, okay?
So why is there a y dx when there's no x available? As if there is no change in x?
So this is a relationship between x and y. So you should think whenever we write y, we mean y is a function of x. You see what I mean? So what's the goal? I want to determine what this function of x is. You see what I mean? There's always going to be at least two variables in differential equations. One dependent variable that we're searching for, and then the independent variable that it depends on. Is that clear?
No, because it seemed like you would have that in the first, whatever you call it, the first,
This equation?
yeah.
Well, what if, so like I said, in order to move from Leibniz notation to differential notation, it's simply a matter of an algebraic manipulation. If you treat this as if it were a fraction and multiply by the denominator, right? If I multiply this equation by dx, dy dx times dx, if they were fractions, would be dy. You see, y times dx is y dx, 0 times dx is 0. So I'll explain what this means a little bit more when we encounter it, when we talk about how to solve it, but for right now, I'm just telling you, if you'd like to move from this notation to this notation, treat the derivative like it's a fraction, and then continue from there. Okay? So what are the advantages? Well, many of the equations that we're going to solve, it's going to be much easier to work with differential notation, okay? But one of the drawbacks is this trick doesn't work for second order derivatives, okay? If you've got a second order derivative like d2y over dx2 plus something else, you can't multiply by two differentials, okay? So we can only write differential equations using differential notation if the equation's first order. It's impossible to use differential notation if it's higher order. Okay? So it's, let's say, useful but limited to first order. questions so far? All right, so we'll spend most of the semester discussing